All right, guys, we're going to finish the second part of our discussion on ethers and epoxides. So let's talk a little bit about epoxides. This is an epoxide. I guess you could say it's kind of like a cyclic ether. The only catch is that the ether portion kind of resembles a three-sided ring. Now, in naming epoxides, it's kind of like naming anything else that we've come in contact with so far. Let's say that I have 1, 2, 3, 4, 5 carbons. Okay. So 5 carbons, longest continuous chain. Indication is that it's derived from pentane. You fill in my hydrogens. Make my little ring. And you can see where the epoxide is. Because the three-membered ring is between carbons 2 and 3, we would call this 2,3 epoxy pentane. That's it. You just have to use the prefix epoxy and designate where the epoxide is within the chain of carbons. It's just that simple. Okay, so I guess that leaves us with talking about how do you make an epoxide. Well, there are 2 accepted methods. There we go. So, number 1 is what we would call peroxidation of alkenes. And what that means in English. Let's say you have an alkene. Like so. We're going to react the alkene with what's called a peroxy acid. So it's kind of like a carboxylic acid, except you have an extra oxygen. Now, because of the length and complexity of the mechanism, don't worry, we're not going to go through that. The only thing I need you to know is that with any alkene in the presence of a peroxy acid, you'll get an epoxide. And as a byproduct, you'll get the reduced form, which is a carboxylic acid. So the peroxy acid essentially is reduced down to a carboxylic acid. And we'll get our peroxide. Now, don't worry too much about the carboxylic acid. I believe that's a couple of chapters from now. So that is what we will come away with. Okay. The second way of making an epoxide is probably the more popular way. And this is through halohydrins. Now, just to walk you down memory lane, you may recall that if you have an alkene, for example, let's say we have 2-butene. In this case, it doesn't really matter whether it's cis or trans. Now, if I react an alkene with a molecular halogen, say bromine, you may remember that one of the halide atoms is going to form this almost imaginary dipole. Okay. And we're going to get something that looks like this. Remember that? And if I now allow this intermediate to react with water, and water in this case, we need the water, that's our polar solvent. Okay. The water kind of breaks this ring structure up, and we should get something that looks like this. And then, of course, if we just wash the complex with water again, we get rid of this nasty extra proton, and we get a halohydrin. Now, you may remember making vicinal dihalides, in which case we would have broken this ring structure up with the other bromine. Well, this is called a vicinal halohydrin. Okay? All right. Now, here's the cool part. What if I take, give myself some more room, what if I were to react this hydroxyl with a strong base? Well, considering that proton on the hydroxyl here is subject to removal by my strong base, I probably will get something that looks like this. It looks remarkably like an alkoxide, doesn't it? It's because it is. Now, here's the fun part. Look at this carbon attached to the bromine. Bromine's kind of electronegative, isn't it? Which means this carbon should have a partial positive charge, and there's probably a small dipole moment attached. Well, this alkoxide is somewhat nucleophilic. This carbon is electrophilic. Watch this. You get internal rearrangement. And there is your epoxide. So 4 carbons, the epoxide is between carbons 2 and 3. So 2, 3, epoxy, butane. Okay? All right. Well, I think that opens up some new questions. Okay, once we get this epoxide, what can we do with it? So let's talk about some of the reactions that are associated with epoxides. So, first reaction. Epoxides are really susceptible to Grignards. Grignards love epoxides. Let me give you an example. Let's say I have an ethyl Grignard. So that's my ethyl Grignard. And let's say I'll take something simple. How about this? This particular epoxide has a special name. This is called ethylene oxide. Even though, yes, it's an epoxide, but that's what we call it. Okay, so the Grignard would attack one of these carbons in the ring, thereby forcing a break in the bond. And we'll get this. And then all we have to do is wash it with water or dilute acid. I usually use dilute acid. And we will come away with an alcohol. Now, is it a coincidence that the alcohol that's produced is primary? No, no. Um, it really depends on where the epoxide is. The smaller the epoxide, the more reactive that it's going to be to the Grignard. So usually you will only see Grignards reacting with ethylene oxide. That I can't recall seeing Grignards react with any bigger epoxides. So, what else can epoxides do? Well, epoxides are very prone to nucleophilic attack. Now, the majority of the time when you do see nucleophilic attack, it tends to be catalyzed by some kind of acid. So we usually say something like acid catalyzed nucleophilic attack. So, trying to think what would be a good one. Ah, you know what? Why not just use the epoxide that we just had? So, if I had the 2,3 epoxy butane, if I were to react this with hydronium, that's an acid. It also will eventually be a source for our nucleophile too. So, as you would expect, the hydronium will protonate the epoxide, and the protonated epoxide would look pretty much like this, as you would expect. Now, what do you think the water is going to do? Yeah, the water is going to act as a nucleophile. Now, in this case, since the molecule is pretty symmetrical, does it matter from what side water strikes? No, not in this case. In some cases, it might. Um, the nucleophile will always strike on the least hindered side, if that makes any sense to you. So, myself some more rum. And what we're going to come away with is going to be well, at least the makings of a vicinal diol. As you can imagine, a diol is just an alcohol with two OHs. But I figure you already could kind of deduce that. And there we go. So in this case, vicinal diol. Now, in this particular case, water served as my nucleophile. Does it have to be water? No. Um, anything almost anything can be a nucleophile. So alcohols can be a nucleophile. Um, Halogens can be a nucleophile. Um, Other ethers could be nucleophiles. It really depends on what you're playing around with. Well, that's pretty much all that I wanted to say about ethers and epoxides. I know compared to the first part of our discussion, this was pretty short, but I think this gives you guys enough information to try to digest. So, if you have any questions, let me know. And our next discussion will be on aldehydes and ketones. Thank you for your attention and cooperation, and y'all take care.